In this video, I want to have a look at vector arithmetic, so multiplying the vectors by a scalar or a number and adding or subtracting vectors to each other. So there's a couple of different ways you can think about or visualize vectors. Through this video, we're going to do everything geometrically. The first thing I want to have a look at is scalar multiplication. So when we're talking about scalars in this context, we're just talking about numbers. So taking a vector and multiplying it by a number. So if we've got a vector p and we've got a scalar which we're going to represent with the Greek letter lambda, then if we multiply them together, lambda p has length, the absolute value of lambda, times the absolute value of p. So that's the length of our original vector multiplied by the absolute value of lambda. Now, if lambda is a positive number, then when we multiply our vector by that positive number, it's going to end up pointing in the same direction as our original vector. But if lambda is a negative number, then it's going to switch the direction. So it's going to be pointing in the opposite direction to our original. If lambda is exactly equal to 0 and we multiply by any vector, then we're always going to end up with the 0 vector as our answer. So from all of that, whenever we multiply by a scalar, we're always going to end up with something that's parallel to our original vector, but it might be pointing the opposite direction or the same direction depending on whether that was positive or negative. And like we said in the last video, even if we multiply by 0 and we end up with the 0 vector, we define the 0 vector as being parallel to every other vector anyway. So just to give you an idea of what you're thinking about when you're visualizing scalar multiplication, if we have this vector here, let's call it p. If I were to multiply that by 2, this would be the resulting vector here. So this would be 2p. So it's moving in exactly the same direction, it's parallel, it's pointing the same direction, but it is exactly twice as long. This one here would be 0.5p. So again, it's pointing in exactly the same direction, parallel, but it's exactly half the length of the original vector. This last one here would be minus 1.5p. So this one is pointing in the opposite direction because our scalar was negative, so it's pointing the opposite direction now, but it is still parallel to all of these ones. And it's exactly 1.5 times the length of the original vector. All right, let's have a look at vector addition next. So we're talking about adding one vector to another vector. So what that means is when we're adding vectors, we're describing one translation, so one shift from that first vector, and then following it immediately by the second vector, the shift that the second vector describes. And our answer will be one single vector that describes the overall shift, the overall movement. So there's two ways of visualizing this. We're going to have a look at both of them. So the first method is referred to as the triangle method. If we have two vectors p and q and we want to figure out what p plus q is, then we're going to draw our first vector, then we're going to draw our second vector, but we're going to start the tail of our second vector wherever the arrowhead of our first vector ended. Then we're going to draw a vector from where we started, so the tail of p, and we're going to join that onto the arrowhead of q. So let's have a look at what that looks like. So in our example, we have our vectors p and q. If we want to add those, like we said, we want to have a look at the shift that this vector is describing, and then also the shift that this vector is describing. So we're going to draw p, so I've drawn that again here. Then from that endpoint, we're then going to draw q. So we've got q drawn there. To find our answer, our new vector, our addition, we'll be joining this point here to this one here. So like we said, making this shift that p describes, immediately followed by this shift that q describes, could be described in one step as this shift here, so moving this length in this direction. So that's what this new addition vector is describing. The second method, or the second way that people visualize this, is called the parallelogram method. So for two vectors and we want to perform that same addition of p plus q, then we're going to draw p, but this time we're going to draw q starting from the tail of p, so they both have that same starting point. And then we're going to complete the parallelogram and draw in the diagonal. So I've just used the same vectors that we had in our last question. I've drawn p here, and then starting from that same starting point, I've drawn q from there. What we're going to do now is we're going to make this into a parallelogram. So we're going to replicate P up here and replicate Q up this direction. So we've drawn our parallelogram in grey there, and then drawing in that diagonal gives us our addition, our P plus Q. Now you can see that these two methods, the triangle and the parallelogram method, are essentially the same thing, because in a parallelogram, the opposite sides are parallel and equal. So that means if this is our vector Q, then this grey line here is also Q. So then if we ignore this part, then we've got P plus Q, and we've got that line across there to find our sum. So that is just the triangle method then again. Now, two important things about addition with vectors is that addition is commutative. So when we're talking about numbers and we say addition is commutative, we mean things like 3 plus 5. Well, that's exactly the same thing as 5 plus 3. They both give you 8. It works the same way with vectors. So when we had this example before, we did P plus Q, and that gave us this blue vector here as P plus Q. Now, if we were to do those the other way, if we were to start with Q, and then from there, using our triangle method, then we'd add P to that, the vector that we would get is exactly the same. So you can see that these two blue lines are pointing in the same direction and they are the same length. So addition is commutative. Secondly, addition is associative. So again, if we think about numbers, if I have, say, 1 plus 2 plus 3, it doesn't matter whether I think about that as 1 plus 2 and I figure that out and then I add the 3 onto that answer, or if I do 1 plus and add the 2 and the 3 together first. So do the 2 and the 3 and then add that 1 on. That doesn't matter. And the same thing works with vectors. So for example, if I had 3 vectors, P, Q, and R. Now if I add the P and the Q, that would give me P plus Q like we've been looking at. So now in here, if I have my P plus Q, if I add on a vector R to that, then this vector here would be P plus Q plus R. So that's my green vector there. This one instead, this here is my vector Q, and this is my vector R, so the same vectors we were using in this part. Then this blue line would give me Q plus R. Now over here, if we have that Q plus R written in here, if I also start with my vector P down here, so I've got my P, and then using that triangle method, I'm going to add my Q plus R, then this green line here would give me P plus my Q plus R. So you can see that that green vector, that line, is exactly the same length and direction in both of those. So addition is associative with vectors as well. Okay, the last thing we want to have a look at is vector subtraction. So if we want to find the difference between A and B, two different vectors, then we can do that by taking the sum of A and the opposite of B. So what that means is that if we're writing A minus B, we could think about it instead as A plus negative B. So the way that makes most sense to me to visualize this is if I have a vector A and a vector B and I want to subtract, then I'm going to take my vector A and I'm going to do the triangle method for addition, but I need negative B instead of B. So what that means is it's the same length, but it's going in the opposite direction, so down this way. And then we just join them together like we were doing for addition. So then you can see our blue vector here would be A minus B. Now this isn't the only way to geometrically represent a subtraction. Let's have a look at another. So the other method is that we can draw both our vectors A and B and start them at the same position so their tails are joined. And then we can draw a vector from the head of B to the head of A. And that will give us that same vector, that same subtraction vector that we had using our other method. The reason I don't like this method so much is that people tend to get a bit confused, especially in that last step, as to which direction they're drawing their vector, as whether they're going from the head of B to the head of A or the opposite direction. And also the putting the tails together kind of starts us off looking like the parallelogram method for vector addition, which can confuse people as well. But there are those two different ways of thinking about it. Okay, so that's having a look at vector arithmetic.